Here's a picture of me. I got some kind of crazy camera on my eyeglasses, and I got a big battery pack and radio transmitter on my rear. Not exactly Google Glass, but that's not what we're going to talk about today. I want to talk about the difference between this image and this image. I'm sure a lot of you had the fun of sitting in a boring Zoom meeting and playing around with aliasing on your striped shirt. That's what we're seeing here. The image on the left is a downsampled version of the image on the right. You see that even the direction of the stripes has changed due to aliasing, and definitely there's a lot of distortion. Today we're going to talk about what makes this happen. Computational imaging. Episode 6, Discrete Forward Models. Today we examine in more detail the relationship between discrete samples and signals. Here we see the canonical example, a focal plane with square pixels. So we have an image we'll call f of x that comes from a remote object and onto our focal plane here. And we're going to integrate that image over these square pixels. The pixel sampling function, as we call this p sub m of x, integrates x over its pixel region to give us discrete measurements g sub m. We've explored various strategies for representing f discretely, including Fourier series, Shannon sampling, and wavelets. F is represented on some basis, which could be, for example, the Shannon basis, as shown here. Now, previously, we've noticed that we can't really measure these discrete samples of f at specific values because we don't have delta function sampling. But nevertheless, we can represent f in this way, and once we've represented f on some discrete basis, we can get a model for our measurement system. So we have our discrete measurements. Here we've generalized the measurement function to be h sub m of x, talking about a general impulse response, and we have a continuous f. But we substitute in the discrete form of f, and then we can turn this integral transformation into a matrix vector product, where g sub m is the sum of f dotted with these coefficients h sub m and n. H sub m and n we get by integrating over the discrete basis for f, so it's equal to the integral of the sampling function h sub m against the basis function phi sub n for x. And this allows us to turn our forward model into a discrete form, where now it takes the simple form that the vector of measurements g is equal to the matrix forward model h times the vector of representation coefficients f. F is generally not known, but the point of our measurement system is knowing the forward model h and the measurements g. We can try to estimate f from the measurements. Quite often we deal with shift invariant measurement systems, where the pixel sampling function is the same for all pixels. It's just shifted by the pixel pitch, which means our measurement takes the form of a convolution. If we think of this in terms of the matrix coefficients, it turns out the matrix is tuplets. The matrix coefficients depend only on the difference between m and n and not on their absolute values. Now, we've seen that when we have a shift invariant measurement system, that we can turn it into an algebraic form consisting of the product of the Fourier transform of f hat of u, with the transfer function p hat of u, the Fourier transform of the pixel sampling function. Now, in our measurements, we don't have the continuous values of the measurement system, which would allow us to take the Fourier transform and get this form. But we can take the discrete Fourier transform, which we've defined as shown here as the product of this discrete Fourier transform kernel summed over the measurements. And we'd like to relate this discrete Fourier transform to the continuous Fourier transform of the underlying measurement function. To do that, we substitute for the measurements their representation as the inverse Fourier transform of the Fourier transform. So this is the Fourier transform of the measurement function here. It would be the product of those two Fourier transforms. This is the inverse Fourier transform kernel evaluated at the sample point m delta. And now, instead of conducting this integral to get back to our measurements, we'll evaluate the sum over the discrete Fourier transform first, which turns into this periodic sinc function that we'll discuss in the next slide. So if we look at that sum of the kernel of the discrete Fourier transform and the kernel of the inverse Fourier transform, this is a geometric series. So a geometric series is something of the form from, let's say, k equals 0 to k equals big K, r to the k, that has the form 1 minus r to the k, big K plus 1 divided by 1 minus r. This exact formula is applied here on this series to recover this, what turns out to be a ratio of sine functions. The period of the sine function in the numerator is 1, or actually it's 1/2, since our frequency would be, it would be 2 actually, because our frequency is 1/2. The frequency in the denominator would be 1/2n. So this is a very low frequency, or a low frequency long period function in the denominator and a high frequency period in the numerator. When the numerator and the denominator go to 0 at the same time, we get a ratio of zeros, which turns out to be very similar to the sinc function. So this is very similar to just a periodic sinc function. We can approximate it, in fact, as, in the region of a 0, the numerator would act like a sine and the denominator would act like a constant. It'll behave like a sinc, and if n is large enough, that sinc behaves like a delta function. So it will turn out that the discrete Fourier transform of our measurements is going to evaluate this integral for the inverse Fourier transform at delta functions where u is equal to m prime plus n over x. Those would be the coefficients of our delta function. And so we get a periodic representation of the continuous Fourier transform of the underlying measurement distribution from the discrete Fourier transform of our actual measurements. So this is periodic because n here is an integer, and for all integers n, we get a copy of the Fourier transform of the signal centered at m prime is equal to the integer n times n divided by x. Here's what this looks like in Fourier space. So we have here, the plot of the Fourier transform of the continuous representation of the underlying measurement distribution. It looks like this, but we see copies of it at separated by this value n in the index space, where this would be the m axis. But u, we saw, is equal to something like m over x. And so if the period in the discrete index is n, the period in u is equal to n over x. X here is the extent of the spatial sampling function. It's n times delta, where delta is the pixel pitch. So the period in u is 1 over delta. So we see these copies of the Fourier transform of the underlying signal distribution separated by 1 over delta. They don't overlap if the center to the edge is less than or equal to 1 over 2 delta, which is the Nyquist sampling rate. So as long as we sample at Nyquist, we would be able to separate these Fourier coefficients. If we sample at less than Nyquist, then the distributions overlap, and we see high frequency coefficient, or high frequency pieces of the Fourier transform of the underlying signal distribution leaking into the bandpass for each of the copies of the Fourier transform. And what that will cause is that high frequencies will become low frequencies in our reconstruction, as we'll see in just a second. If aliasing is avoided, then the discrete Fourier transform of our measurements is equal to the continuous Fourier transform of the signal distribution f hat of u, and times the continuous Fourier transform of the pixel sampling function p hat of u, evaluated at u is equal to m over x, where m is the index of our discrete Fourier transform. All right, so let's look at some pixel functions to see how this might work. So one thing we can choose in our measurement system, in a computational imaging system, what the pixel or the sampling function might look like. And so we've suggested that in many cases it's just a rect, that we integrate the signal over the range of the pixel. So here the horizontal axis is in units of delta. So this is x equals 0 delta, and at x equals 1 times delta, we'd have another sampling function that would look like this. And we have this periodic rect sampling function. Another example shown here is that the sampling function consists of 3 disjointed rects. They have the same area as the single rect, but they're separated out. This use of 3 pieces could increase the bandpass of the system by using smaller sampling functions, but have the same number of samples. So we still have a period that this distribution is centered at x equals 0. At x equals delta, we'd have another copy of that, which would have a lobe here and a lobe here and a lobe out here. And then we can repeat that pattern periodically, and we still have orthogonal sampling. And then we can evaluate what that looks like in terms of its impact on our signal. And we could even choose more complicated patterns in order to get an interesting spatial spectral response. The third example is that the pixel sampling function is a Gaussian. So it looks like this. This is smoother. It's going to have a smoother transfer function, which may allow us to manage aliasing in a more intelligent way. Let's look at what the transfer functions look like on the next slide. So here, the green curve is the Fourier transform of the 3-lobe system. Interestingly, it goes to 0, so this would be at the Nyquist frequency, the Nyquist sampling. The horizontal axis here is in units of 1 over delta, so this is the frequency in units of 1 over delta. To avoid aliasing, we need the measurement bandwidth to go to 0 at 1 over 2 delta, which would be here. Now the measurement signal, of course, is the product of the Fourier transform of the pixel sampling function, the transfer function, times the signal. So if we were lucky and the signal went to 0 at Nyquist, the signal bandpass went to 0 at Nyquist, it wouldn't matter that we have all this high frequency transfer in the pixel sampling function. But if the signal does not have a limited bandpass, then the area out here where we have substantial non-zero bandpass in the pixel sampling function is going to create aliasing in our estimated signal. Now, the 3-lobe system has the nice property that the main lobe goes to 0 right at Nyquist, and it may be that if the signal values, the signal bandpass is not large past the bandpass, that this could be better in some ways than the use of the single lobe system, which is the blue curve here. That's a single lobe rec, which also has substantial bandpass past Nyquist. The Gaussian system goes more smoothly to a 0 bandpass. It still has this region here where there's alias signal coefficients or alias signal power, but it may have a less of an aliasing artifact in the signal. So the point of this slide really is just to show that there's a lot of potential for designing the bandpass and the impact on the signal by designing the pixel sampling function. You could, if you wanted, make the pixel sampling function equal to a sinc, in which case the bandpass would be flat and then go to 0 at right at Nyquist. That would be highly desirable, but it's not easy to make a pixel sampling function like a sinc. More commonly, based on the electronics of sampling, we're going to sample locally for each pixel, and as long as the pixel sampling is limited to the region of the pixel pitch delta, the bandpass of the pixel is going to extend well past delta based on the Fourier uncertainty relationship. So in general, aliasing will be a problem that we'll have to deal with in looking at signal sampling. In the next lecture, we'll talk about some strategies for changing the pixel sampling in a non-shift invariant way to deal with this problem, and there are also ways we could use to structure the nature of the bandpass in ways that we might be able to de-alias the signal. But for present purposes, it's just a real interesting issue for us to be aware of and think about. Let's look at an example of an actual signal. Here, the sampling function is assumed to be a delta function, so we're just going to look at the effect of aliasing on the signal. So we have a single frequency cosine, and we've modulated it by a Gaussian of width with variations of 3, square root of 10. So there's a single frequency. If we take its Fourier transform, we're going to see the two frequencies, -1 and +1, corresponding to the cosine modulation, and then the Fourier transform of a Gaussian is a Gaussian. So the envelope on these two frequencies and the cosine is a Gaussian. Now here, the period of the cosine function is 1, so the Nyquist sampling, the Nyquist period would be about 0.5. We've sampled at a period of 0.1, so we've way oversampled. The sample data is shown here on the left. We've interpolated the signal using a B-spline, which we use to approximate the Shannon sampling, to upsample it and look at the underlying signal in the middle. And it looks great at this sampling rate, and then we take the Fourier transform of the upsampled data to see what the Fourier transform should look like, which is very consistent with the underlying signal. Now, if we sample at less than Nyquist, here we're sampling at 0.45, so 10% less than the Nyquist frequency, and what you see is that, basically our Fourier transform is still at 1 - 1, but it's hitting the edge of the band, and so we expect to see some aliasing noise, and we do see that we're getting a kind of modulated envelope, a beat frequency in the reconstruction that decreases the center of the frequency, and that's not recovered when we interpolate to upsample using the sampling theorem. If we undersample even more, so we're sampling with a period of 0.65, what happens is that the high frequencies are shifted to lower frequencies because they're undersampled and aliased. So here's our sample data, and our interpolated data looks great, but it's at the wrong frequency. When we look at its Fourier transform, the frequency is shifted to -0.5 and +0.5. So it's shifted by a factor of 2 by this undersampling and aliasing. Here's a more complicated signal. So in this case, it's also a Gaussian envelope, but now it's cosine of x squared. So at the edges of the Gaussian, we're out here close to 10. The period is going to be the effective period. The effective frequency is going to be around 5, which means that Nyquist sampling should be at about 0.1. Now, in this particular signal, we want to simulate what happens when we have a finite-sized pixel. So we're going to integrate the signal against pixels, which are going to be rectangular functions. In the top curve, it's rectangular width 0.3, and in the middle curve it's 0.15, and the bottom curve is 0.07. Now here we've assumed that we have 100% fill factor, which means that the pixel pitch and the pixel extent are equal to each other. So if the pixel width is 0.3, the pixel pitch is also 0.3, and so what we find is that when we have the pixel that is larger than Nyquist, the high frequency terms here, when we integrate a rect over this area, are averaged out. So we don't see high frequencies; we only see low frequencies consistent with this sampling. And when we interpolate and look at the Fourier transform, we find that we've reduced the band. Both as an impact of the Nyquist sampling, or the sub-Nyquist sampling, and the finite bandpass of the broader pixel. As we decrease the pixel size, and this is all actually integrating the signal versus these pixels using numerical integration rather than Fourier methods, we see that we get higher frequencies, and then when we get sub-Nyquist, we get a good reconstruction of the underlying signal. Now, it's not necessary, of course, that the pixel pitch and the pixel extent should be the same. So, for example, I could have 0.07 width sampling functions, but I could make the pixel pitch somewhat larger. And what will happen then is that we'll still have a high frequency bandpass, but we'll have aliasing from the undersampling, which would make the bandpasses overlap. Here's what happens, well, for example, when we take the 0.07 pixel, but only measure every fourth one. So now the separation is going to be 0.28, and so the pixel pitch is about the same in these two curves, but in the top curve, the pixel extent is 0.3, and in the bottom curve, the pixel extent is only 0.07. And what you see is that in this high frequency area out here, the smaller pixel picks that modulation up, but it picks it up at an effectively lower frequency because it's undersampled. And so with the bandpass is greater because than it is, or maybe it's just a little bit greater than when we have a larger pixel. But the signal, the high frequency signals appear as low frequencies because of this aliasing effect. So the point of all this really is just to, first of all, in today's lecture, show how we can create a discrete forward model by representing f on a basis, and we've been through these examples of different basis functions, or different ways to represent a continuous function on a basis. And then looking at the discrete measurement systems, we can create a algebraic forward model, G equals HF. When we do that with shift invariant systems, this aliasing is going to be a problem. Aliasing is also a problem if the system is not shift invariant, but the structure of it is a little bit different. Basically, aliasing is a artifact of the fact that our discrete basis is incomplete. The signal will have features that are not described within the measurement features of the system, and those features may project into the measurements in ways that create artifacts, and we'll just continue to discuss that throughout the course. Now, next time we're going to look at shift variant systems, and so shift variant systems, for example, include systems that are 3D-dimensional imaging systems using projection tomography. The movie you see at the upper right here is a 3D reconstruction of a dancer created with a camera array, but created by back projection, so that because you see the full volume around the dancer is created, and we can rotate and spin the dancer and slice the volume. That's because we've taken projections, line integrals through the volume, and back projected them to create a 3D model. Now here on the right, we show a model of a radon transform where we look at line integrals through a region, so that we're going to measure as a function of distance along a line, and so L would be distance from the origin, and we'll integrate along these rays to get projections through a region. These measurements are not shift invariant, and so we'll have to think of them in a algebraic form, but we can still find ways to analyze the quality of the forward model for these algebraic systems. So basically, with the shift invariant system, this transfer function is a measure of the quality of the system, both in terms of what frequencies it passes and what frequencies it aliases. We need to come up with ways to analyze systems that are shift variant similarly, and for that purpose we'll use the singular value decomposition, which we discuss in the next lecture.